Hello everyone. Today we are going to solve today's LeetCode daily problem. To maximize spanning tree stability with upgrade. What the question states that you are given an integer n representing n nodes number from 0 to n minus 1 and the list of edges where edges I, u, I, vi, si and must I. Okay. Ui and vi the indicates an undirected edge between nodes ui and vi. Si is the strength of the edge. Master is an integer 0 or 1. If master 1, then the edge must be included in the spanning tree. These edges cannot be updated. Okay. You are also given an integer k, the maximum number of upgrades you can perform. Each upgrade doubles the strength of an edge and eligible edge width. Okay, let's see this. The stability of a spanning tree is defined as the minimum strength score among all edges included in it, right? Return the maximum possible stability of any valid spanning tree. If it is impossible, return minus. Okay. Uh, Basically, something related to spanning tree, we are given a graph with some edges, where edges have some properties that UIVI denotes the node which the edge connects. SI is the strength of the edge, and master is a Boolean value, basically denotes that master. If master is 1, then the edge must be included in the spanning tree. Okay, we don't have any choice, and these edges cannot be upgraded. Okay, so this is very straightforward. Uh, and for the rest of the edges, there is a value k, the maximum number of upgrades you can perform. Each upgrade doubles the strength of an edge. Okay, so the edges where master is 0, basically, there we have flexibility, right? Like we can include the edge or can upgrade the edge, but the upgrade operation can be performed almost k time. Okay. And in one operation, what we can do, we can upgrade strength of the edge to double its value. And okay, and each edge can be upgraded at most once. Okay. So basically, we can't upgrade a edge more than once. The stability is basically minimum strength of the score. Okay, written. Okay, got it. So basically, we have to form a MST with certain upgradation where some restriction is there. The stability is minimum of the strength, and we have to maximize that minimum. So whenever we have to maximize the minimum or minimize the maximum, the only topic comes into our mind is binary search. So we're definitely going to do binary search here. Okay, let's break down the problem. So basically what we are said that we have given some graphs like some node edges, some kind of this, okay, maybe some random graph, and every edges has some strengths and some boolean like must. If it is, it should include, like if must is 1, then we have to include it. Okay, we will definitely include. Suppose we are including this, we are including this. Now, uh, from the rest of the edges, we have to find the MST, right, with certain upgradation. So, firstly, we have to know how to find MST. Forget about all these complications or restrictions. Like, first you have to know how to find MST. So, eh, there are two algorithms. One is Kruskal and another is something related to. That's not okay. So we are going to use Kruskal here. Okay. In Kruskal, what we do, we basically sort the edges uh, according to their values and then greedily choose the smallest one and then try to add that to the tree. If that is a valid edge, mean the edge does not form any cycle, we simply include that edge or otherwise we just ignore that. Okay, here also we are going to do that. What will be our idea? So basically, first of all, we need to basically the aim is basically edge size just dot height. Now, first of all, I need to check that uh, okay. So first we need to check that we are going to take the edges which are like which we have to must have to take, right? So that edge should not make any cycle. So if any cycle found in must or like so basically if there is already any cycle in the edges which we must have to take, we never can form a image, right? Basically, we can't form a tree actually if like the edges which we have to take, if that forms any cycle, that won't make any tree, no? Basically, if a cycle is there mm, in n m edges, then simply return -1, right? Now, what we are going to do? We're going to do binary search. So left value is 0, right value. What should be the high? Basically low and high. We are going to do high. High is basically here we are taking exclusive boundary like low comma high. Where like high is bad. Like high is not possible to make answer, right? So what is the constraint here? So strength can go up to 10 to the power 5 and we can upgrade the edges so we can double it. The answer maximum can be 10 to the 2 into 10 to the power 5. So high will be 2 into 10 to the power 5 plus 1, right? So now while high is greater than the plus 1, very standard binary search we are going to do mid equal to low plus high by 2. Right. Now I have to figure out like if it is like is there any valid MST for which the mean value is greater equal to mean, right? So if possible, if such tree exist, then we simply update the low to mid otherwise the high will be maintained. Now, if such low exists, then we will simply return low, otherwise return minus. That's all. Now we will write function if possible. Here we will take a lower bound and we'll return a boolean value like is it possible to achieve this lower bound? Okay, let's write some private function. First is each cycle executable, each cycle, mm, then vector 10% execute. Let's keep it constant, right? Another thing is there the vector is in this format, so it's better to extract. No, we will just extract this thing. That constant vector in V. We will simply return couple of V0, V1, V2, V, V0, V1, V2. We are simply basically extracting these values from vector. Okay. Now we need a DSU class, right? So for this question, you need like you should have a prior knowledge of DSU. DSU basically is disjoint set union. Secondly, disjoint set union. So from the name itself, you can understand that it will unite two disjoint sets. So if you have two disjoint sets and you want to unite them, you need this data structure. And how will we use here? Like to check if a edge, if we connect, if we add a edge to the tree, if it's form any cycle or not, to detect that, we will use DSU here. So basically, if the two vertices of that edge is already in the same set, that means if we like here, like these two edges already exist now. So now for this third edge, if we connect this will form a cycle. So how to find that? Like we will query this vertex and this vertex and uh, we'll try to know that if these are already connected or not. If these two vertices are already connected, so we will simply ignore this edge. So we will simply make a class DSU. Now we need some public and private function. So we need the size and basically for DSU we need two vectors. One like contains its parent and another contains its size, like size of the set, right? But here we will use only single vector which will contain both the details like the parents and the size. So DSU you can one way. So we made the constructor. Now we need some function. We need merge into point V. It merges to set containing U and V. So in um, x equal to basically find U, comma y equal to find V. So x and y are basically leader of the sets containing U and V respectively. Now if x equal to y means both the leader of the two sets are same means these two elements lie in the same set. So we don't need to merge, we just return false to indicate that the merge operation has not like been occurred. And otherwise what we will do, uh, we if like minus fx less than minus fy, we will swap x comma y. What is this basically? This is a concept of like small to large merging. If we are merging two sets, will always merge the smaller set to the larger set. It will reduce the time complexity. So basically, I think there is a law small to large merging. Yeah, I think. You can refer to this blog like where it is sub presets using small to large merging. Basically, it is useful in the tree where when we merge two sets or something like if we merge smaller set to larger, it will reduce the time complexity, right? So then we will update the size like fx plus equal to fy and further of y is not on we can do right. Bool same individual. What does same do? Same basically find if u and v are in the same set or not. Does u and v lie in the same set? So return find of u equal to find of v. Now in size into it basically return the size of the set containing u. So return of find of u. Yeah. Now I need to write the find function. So find the leader of the set containing u. Or return if f of u is negative, then u otherwise f of u equal to find the physical. So we're doing path compression also here in the file. I think let's look. So this is our DSU class, so you can like search on the YouTube and learn about it, like how DSU work, uh, another place. So now we need to write here each cycle. Na? So we will take a DSU of inside. We will simply traverse from all to all the edges. We will get the extraction Q, V, S, and 1. We will to extract edges of all. If must equal to 1, okay, and DSU dot same U comma V. Wait, if must equal to 0, we will simply continue, right? Otherwise must is 1, so then if DSU dot same UV, we will return true. Otherwise we will merge. If no such condition found, so we will return false. That's all I think. Yeah. So now here we come to the each possible part. So we have to check that if it is possible to upgrade such a way so that the minimum strength of the MST is at least lower bound. So let's take a DSU here. Also extract UV minimum. Sorry. Now if not 0, then continue. Basically what we are doing, we are basically taking the edges where mask is 1, so we have to take it now. So we have no choice, so we are going simply taking those edges. So mm, now what I need to do, so if strength is less than lower bound, then return false. There is no cycle we are here, so we will simply merge you gonna be right. So what will be going on here, we take the must take edges. Now we have to go for the other edge. For the remaining edges, we will greedily find the edges with larger value, okay, and upgrade it if necessary. So for here, if must one, then continue. Otherwise, what we will do, for that we need to sort the edges. No? So we are going to sort the edges. V1 also insert V2. So what we're doing, we're basically sorting the edges based on their strengths. So return B1 of strength is 0, 1, 2. So 2 should be greater than equal to. Mm. So we have sorted edges based on their strength. So more strength the edge have, it will appear first. Now here if strength is greater or equal to lower bound, we won't check anything. We will just simply mod. Like it may occur in the same set, but we don't care. Uh, Otherwise, we have to check something that like it is not greater or equal to lower bound. Na? So we have must have to perform a upgrade operation. So when we will perform a upgrade operation, if it does not like if it a valid edge means it the adding this edge does not create any cycle. So for that we will check if DSU if DSU dot not same event B, then we will consider this thing. Okay, if they are not same, we are good to make an update. So for that we also are limited. We can do at most k updates. Huh? So we need to make a copy of k in k equal to k. Let's make it capital K. Now if our k is already like me, if k is less than 0 or the upgrade also does not work like 2 into s is less than lower bound. What does that mean? Basically we like to take that edge we need to upgrade that edge, right? So if k already finished means we can't upgrade. We don't have enough operation to upgrade the edge. And also if like doubling the edge don't reach our like fulfill our criteria, that means the upgrading also has no like relevance. So we won't upgrade, we will just return uh, false from here. Basically DSU dot not same means that there basically the MST has not completed yet. If the MST has been like already constructed, then there won't be any age where the both of the event we are different. So it is different means that the MST has not been constructed completely yet. But what we have seen that the operation also like we don't have any remaining operation and also like increasing this or upgrading this age won't work. So we are directly returning false because the other ages which are remaining they are less than this value. Na? Basically we have sorted the value in the descending order. If this value is larger than the remaining value, if it won't work, the other also won't work. So we are just directly returning false. And at last, we have to check that the MST has been formed or not. So for that, we will just check that if DSU dot size of any edges, like any vertices, let's say 0, is equal to m unknown. Okay, so that's all. I think that's to do work. Mm, Extract with deduce return type defined. Okay, some problem with extract. Let's check it out. I think not. So maybe here if we run this. Okay, so error is solved, but there is some problem. Let's check it out. So we are basically returning less value than the expected. Okay, that makes sense. What we are doing, okay, we are not basically margin the value, no. DSU dot mark, yeah, I think that should work. Let's submit it. Yeah, it got accepted. So what we have done, we have basically just first checked that what edges we must have to take. If we take that, it will still remain a MST or not. If that edges already produce any cycle, so that won't be any tree, so we will return simply -1. So if there is a cycle in the necessary edges, we will return -1. And then after we sort the edges with the value on the basis of their strength, now we will do simply a binary search where like low is 0, high is 2 to the power 5 plus 1. Why 2 to the power 5 plus 1 I have taken? Like you can find it dynamically also. Uh, how you can find it, like here simply you can look here, go through all the edges, and like whatever edge you have taken, the minimum of that will be the answer, no? Basically I equal to minimum of I comma like edges of I comma 2. If edges of I comma p, or simply extract that a comma b comma f comma mark equal to the edges I. If must 1, then I equal to minimum of I comma if 12. I do. So we have taken a minimum. Now we have traversed over all the edges, and if that edge is must be taken, then we are finding minimum of among that edges. So the answer should lie between 1 and that value, no? So we have binary search over there. So it will also work. Yeah. So after the binary search, we are just taking the checking that if there exists any valid minimum spanning tree for which the minimum value is greater or equal to mid. So if that exists, then we are just simply setting low to it and finding better result if exist. In each possible function, what we have done, we have basically initialized a DSU. Then firstly we took the mass take edges where we have no choice. And if the strength, like in this case, it won't happen. No? Basically here we dynamically basically find the minimum. So this condition never will occur that the strength is less than lower bound. After that, we are just simply merging this. And for the remaining edges, we greedily go over from largest value to smallest. If the value is already greater than lower bound, we will simply take that edge. And otherwise, if they are not same, means they can be a part of the MST. So we will check if we have enough operation remaining or not, and then we will check that after upgradation, can we use this edge as part of the tree? If no, then we will simply return false. Otherwise, we merge uh, add that edge to the DSU, basically to the tree. And at last, we will simply check that if the MST is formed or not by checking if the DSU size is n or not. So that's all for today. Thank you.